my background is I'm actually not in academics anymore. I did my background in theoretical chemistry at the University of Chicago, and I actually worked in the statistical physics of neural networks, back in the 90s. And since then, I've been mostly working in industry, working in places like Aardvark or eHow, BlackRock, lots of different kinds of companies. And one of the things I've found in my practice is that people are really starting to use this deep learning stuff. It's really popular, and you just have, everyone and his brother is trying. There's really a huge interest in machine learning. One of my former clients has been hiring companies to come and teach all the employees how to do, all the coders how to do machine learning. And there's a huge interest in things like Google TensorFlow has just created a tremendous amount of interest. And I'm seeing it in my practice, and so I thought, well, this is something we really got to try to understand. So this is the talk. I'm actually really happy to be here. I've actually been doing a lot of lectures in the business school. I never imagined I would be doing lectures in the business school, but and now with machine learning coming back, what we found is that, we get to do a little theoretical physics again. So I get to be a little more like Sheldon. When I give the talk in the school, I try to explain that there are really 3 ways of looking at these problems. There are engineering ways of looking at it. I kind of call Howard's the engineer. And there's experimental physics. Data science is Leonard. Leonard is really like a data scientist. He's more practical, can deal with people. And then there's Leonard, and which is really where the heavy-duty work is coming from. So the problem started off and try to understand why does deep learning work. It really is this problem of how can SGD possibly work when you're running something like deep learning. Now, if you don't know, is this the original? Oh, okay. So this is the older version of the talk. So I don't have if you know anything about how deep learning works, there are these networks that are that have this complicated energy function, and the goal is to minimize the cross entropy. And so it seemingly is that this is very, very complex, very complex non-convex optimization problem that they're trying to solve. And what it seems to have been observed from a number of groups that have come out and starting to argue, well, it doesn't really seem to be non-convex at all. It seems to be that when we solve these things, you run the SGD solver and it just goes downhill. And it's not entirely clear why this would happen. So what the impetus of this is that there's a recent, so this is the outline of the talk. So what I'm going to do is first talk about sort of what people really think is going on, and a relationship between some old models from theoretical physics called spin glass models, which have been used to try to understand deep nets and why they're working. Then I'm going to introduce something called the random energy model, which is really a simplification of some of the more complex spin glass models people are using, and sort of talk about how that may be a good model for looking at this. And from there, introduce ideas of temperature and regularization and how this plays into the random energy model and something called the glass transition. Then I'm going to talk about another model from theoretical chemistry, which is called the spin glass of minimal frustration, which is an extension of the random energy model and has been used for primarily in protein folding and what are called funneled energy landscapes. And then try to give some examples from deep learning, such as dark knowledge or generative, dark knowledge, and some other examples of what we think may be going on. So before I start, I'll give you a warning. Condensed matter theoretical physics is really about qualitative analogies. There are a lot of simple models. There are toy models. Sometimes we make one like a mean field theory description of something. It's not really a quantitative theory. Theoretical chemistry is quantitative, but a lot of these models are very quantitative, and sometimes you're looking for just a phenomenological description of what's going on. So you're going to see a lot of very simple models which are just trying to give some insight into what's going on, but it's definitely not an attempt to be very quantitative. Okay, so we start off with, this is the important one, what is the deep learning actually solving? Well, you've got this network. It's an energy function which describes these neurons. Usually it's described as being neurons in the brain, and inputs are coming in and neurons are being activated, and there are these hidden neurons in the brain that are being activated, and then there's an output, and then the idea is you minimize the cross entropy. And usually these networks are very, very complicated, and there are all sorts of different versions of them. And as I say, there are tools coming out now like Google TensorFlow, other tools, where you can literally just draw these things on a screen and press a button and you can run them. And one of the questions come up is, what would be a good model for understanding how these things work? And the model which has arisen recently is something called a p-spherical spin glass. And the way the model, I don't know how to make this. Can you help me make this point? The way the model works is that there's an energy function. Here it's called L. And it's basically a linear combination of these xi's, which are random Gaussian variables. Okay, the xi's, and then the w's, which are the spins. And the h is the size of the network. H is really p. This comes out of a paper by LeCun in 2015 where they were trying to explain why deep learning seems to be convex. Why does SGD seem to work so well? So this is his notation. And the idea is that what they do is they take these spins. Usually these are spin up or spin down. But you relax them to be real numbers. And you just put a spherical constraint on them, so they sum to 1. And this is the model people have been using. And this is a very nice model. You can solve it analytically. It can be simulated very easily. This model's been around, for at least 20 years or so. People have been studying this thing. Now, to get an idea what is a spin glass, why is this an interesting model? Well, for those of you who may not be familiar with it, the idea is an old idea in theoretical physics and chemistry. You have an energy function, which is a Hamiltonian, and there are some spins, which are either up or down. And the goal is when you minimize the energy is that all the spins should be paired. So in this case, when the blue is up and the red is down, J is less than 0, that's paired, so that the energy goes down. When you have S1, if S1 were up, it would be paired with red but not with blue. And if S1 were down, it would be paired with blue or not with red. And so the idea that this means that you can't actually solve all the constraints. Hence the term frustration. These are frustrated systems. Because you write down the model, you want to minimize the energy, but there really is no one solution that would work. So this is a typical model of a spin glass. Sometimes physicists call this an Ising model, and there are a number of these things. There's one, for example, called the there's an Edwards-Anderson model, SK model, p-spherical spin model, a whole range of these things. The current result on the p-spherical spin glass seems to suggest something which was sort of suspected in theoretical chemistry 20 years ago, that, and they've proven this analytically now, that if you have this very, very large multi-dimensional optimization problem, and it turns out that maybe there's a ground state to this thing, and there are some local minima. And they're all the local minima are sort of down here in the bottom near the ground state. And as you go up in energy, you have these bands. And the bands are critical points. So all the critical points are basically saddle points of dimension 1, saddle points of dimension 2, saddle points of dimension 3. And they seem to go up like this. So you can imagine when you're trying to solve this kind of optimization problem, you have this very, very complex non-convex surface. But as you begin walking, the solver walks the surface, it can always go downhill. It's just downhill all the way down to the bottom till you get to the local minimum. And so there's sort of effectively what people think is that, well, maybe there are no local minimum in these problems. Maybe they're just all saddle points. And then there's this really interesting graph that comes out of LeCun's paper where they so here's a simulation of one of these p-spherical spin glasses at different sizes. And here's a simulation of a typical multi-layer perceptron, and this is like the test loss. And you kind of look at the two, and they go, oh, these two graphs look kind of the same. Oh, these must be the same thing. And that's essentially the essence of what they're doing, what's going on, and why people are beginning to think this might actually be what's happening. Now, and then there's some other ideas as well. For example, if you've ever run some of these deep learning networks, you know that you have to do something called early stopping. You can't just run them forever. You actually have to stop them at some point. And so this appears to be the idea that you run the thing for a while, and when you stop it, your early stopping kind of gets you down here in the local minima. And really, any of these local minima will do, and you get some good generalization of what you get a model which generalizes well. But if you run it too long, you end up overtraining. You end up in this ground state, and the ground state's this thing you really don't want to be in. So there's some idea that the early stopping somehow corresponds to I kind of go here, and this is my training set accuracy, and if I keep running it, my training gets better, but I have to stop early, otherwise I overfit. And so the sort of the kind of the things that people talk about in very crude sense, I work in industry, things are fairly crude, that it's easy to find the ground state, but it's fairly hard to generalize. And this seems to be sort of the current interpretation. It's easy to find the ground state, but it's hard to generalize. Or, you don't need to find the ground state. Any local minimum will do. You just run this thing and any local minimum will do, and the ground state is overtraining. Well, if you've ever tried to run these things on your own, if you don't have any real deep experience, you find out it's much more complicated than this. You can't just write down a network, press the button, and hold your nose and expect to get something useful. You really have to monitor it very carefully. And the recent results are much more, they're much more specific. They're not as general as this. You're saying something about, look, I know something about the distribution of critical points or the concentrations of the means of an isotropic function, an isotropic random function of a very high dimensional manifold. And so you have to assume that the variables they actually concentrate on their means, and that the thing is actually random, that there's no correlations. And the results themselves, while technically this is a great result, but back when I was doing this, we sort of kind of had an understanding of something called the tap solutions, that there were these energy landscapes and they were funneled like this. And it was never an issue of trying to avoid local minima. That wasn't what people were trying to do. The problem was, what happens when you go to low temperature? That was always the big problem people were concerned about in these models. That you go to low temperature and things just get bananas. So, again, if you look at the problem, you ask, what problem is deep learning solving? Well, you're minimizing you have this very complicated energy function, but you're actually minimizing the cross entropy. So in physics, this means there are entropic effects. You're not just minimizing the energy. In the machine learning, you might talk about something like a divergence. You're minimizing a divergence, you're minimizing a cross entropy. In statistical physics, there's sort of an analogy that you're minimizing a free energy. A free energy is like minimizing a divergence. So you ask, well, how do you introduce the free energy? What's going on? What would be a really simple model for this? Well, there's another model. So this is sort of where I kind of talk about some ideas. I think the impetus of this talk was just to introduce some other ideas. The p-spherical spin model, let's pick the most complex model you can think of and try to work on it. And I said, well, this seems like, this is really complicated, and I get paid by the hour, so I won't be able to do this. But I might be able to do something with a random energy model. And this is a much simpler model, which you may or may not know about. It's very simple. You say, I want the probability of an energy. So I just make it a Gaussian random variable. And the probability of being in the state is 1 over z times the exponential of minus beta times the energy, where z is the partition function and beta is an inverse temperature. And in fact, this is the infinite limit of a p-spherical spin glass. So if you see, and of course the point is, since there's no Hamiltonian, there are no critical points, right? You don't know if there's saddle points, local minima, non-local. It's just random energy. And so you sort of have just this Gaussian energy. And this is a really, really old model. It was introduced in 1981, so even I know about it. It's really old. But what struck me about this original paper is I remember when we worked in protein folding, there was a result, and I think I dug this out of the Journal of Chemical Physics. It's like maybe the late 90s, where you have this plot, which is the foldability of a protein. And using the random energy model, you can compute the foldability of a protein. You can measure it. And it looks, and if you kind of flip it, it looks just like the plot of the multi-layer perceptrons. So, if you believe that looking at a few plots is useful and you can learn something by just comparison of these very complex systems, you see the random energy model, maybe this is not a bad model to try to analyze what's going on in some of these deep learning systems. Now, what do I mean by temperature? Now, what I'm going to do is I'm going to introduce the thing that they don't talk about in this p-spherical spin models are temperature. What is temperature? In energy, in statistical physics or in chemistry, temperature is kind of obvious. It's the temperature. What I mean, and I don't mean in the traditional sense, when some people use statistical mechanics to analyze algorithms. The idea is you have some objective function. So you take E as the objective function, which is the loss function plus the regularizer. You form a partition function. Maybe you form a mean field theory. You take the limits. This is extremely useful. And actually what my advisor suggests, you should do it like, they actually suggested doing this. But this is what I mean. It's very useful. That's not what I'm talking about. What I mean is that the temperature sets the scale of the energy. So the energy scale. So in a very crude sense, if you just say E of t is just energy divided by t, and in a neural network, this is sum of the weights times the activations. So as the temperature goes to 0, the energies get larger and larger and larger in the effective network, and so the weights are exploding. So what I mean by temperature is a proxy for weight constraints or a proxy for regularization. It's a way of controlling the system to keep it from blowing up. So if you look at what's going on in deep neural networks and how people train them, well, this is what you have to do. I mean, you either have to use traditional weight regularization, you regularize it, or you use something like max norm constraints, which is introduced, there's a very famous paper by Hinton on Dropout where they introduced this, or you use something it's going on now, which is batch norm regularization, where you're trying to control the norm, you're trying to really temper the weights so that they don't go bananas. And really also doing things like trying to control the distribution of the local activations of the network, which is kind of like controlling the local entropy in a very crude sense. But what's interesting about the random energy model is that, and this is where things get kind of puzzling, it's where the hand waving really starts, is that the random energy model is a toy model for something called a real glass. So it's a model for glasses. This is why it was introduced. What is a glass? A glass is just, glass, I think I have glass. Sand plus fire gives glass. Glass is a liquid that you cool. So you take a liquid, and if you cool a liquid normally, it will freeze. And when it freezes, the specific volume will shrink. Everything other than ice, which is what everyone's familiar with. Other than ice expands when you freeze it, every other liquid in the world, just about, when you freeze it, actually gets smaller. But when you form a liquid and you supercool it, it doesn't get smaller, it just gets viscous. It's like making a gravy. You make a gravy and you keep adding particles to it, it just gets more and more viscous, but it never actually solidifies. And this is what I mean by a glass. And glasses are really interesting in the theoretical chemistry and physics because they're everywhere. All liquids, if you cool them, can be made into a glass. I mean, there are people who make metals out of glass. They have metal, like you blow glass with sand, they blow metals. So the glass transition is not a normal phase transition. It's not a melting point. It's an amorphous system. And it's universal. It's universal in the sense all physical systems, all liquids can be made into glasses. And yet at the same time, the molecular details actually matter. When you change, the molecular details matter and how you cool the glass matters. If you take a glass, you go to a glass blowing class and somebody blows a glass and the glass is very brittle. But if you cool the outside differently, you can make it hard. So you can make a glass which is very stiff on one end and very brittle on the other. So glasses the details matter, and they actually remember how the way in which you anneal them or cool them gives you different states. You see this in the random energy model because there's basically the entropy goes to 0. If you were in the entropy density, basically this is a phase diagram. This is the temperature. And if you try to measure something like some measure of the entropy, just at this temperature, the entropy just collapses. This is called, in chemistry, it's called an entropy crisis. The system just runs out of entropy. So if you look at, so let's, I'm going to go forward a little. The problem comes up of using the random energy model and looking at things like protein folding. In protein folding, there's this idea that you have a string, you have this protein, and it wants to fold in on itself. It's sort of the string, and it wants to fold in on itself. And if you just let it fold randomly, as if it were just randomly folding, and the energies were random, like a random energy model, it would actually take longer than the known lifetime of the universe to fold. And this is called the Levinthal paradox. It was produced this huge conceptual problem that if you use a random energy model to study complex energy landscapes, you think that's what the energy landscape is. It doesn't seem like it would ever converge. And so we have this issue in the random energy model. We have this picture now, we think, in deep learning systems. Well, there are no trap states. There's nowhere for it to get stuck, except that it might sort of get stuck in these saddle points that are very strangely configured. We have a saddle point which has a very, very long sort of basin. And a lot of the practical work that's going on right now is trying to figure out ways to get through these really horrible looking saddle points. And then, if you get any kind of all sorts of methods, momentum methods, eta grad, RMS prop, all sorts of methods which, Hessian-free methods which are designed to get out of these trap states. And this is the bulk of a lot of the practical work. But the problem is that in a physical system, a lot of people don't believe that a protein could actually fold this way. Now, remember I showed you that plot where you have the random energy model. Oh, 3 minutes? Oh, that's pretty quick. So what happens in a glass is that there's a whole other class of models that exist, whereas this notion that you try to minimize the frustration. So the idea is that if you had a polymer and if you just fold a polymer randomly and it has no connections, it would just have a very flat energy landscape. But if you start adding connections to it, you add connections to the polymer, then the landscape actually gets more and more funneled and it becomes rugged. And this is an old result in theoretical chemistry where people believe that as you start adding these connections, you have many systems. The spin glass is another example of a spin glass or a Adversarial ferromagnet. The energy landscapes become funneled. And the way you can treat this in the random energy model is this thing called the spin glass of minimal frustration. It was proposed by Wolynes and Onachik years ago. And basically, you take the random energy model and you give it a ground state. And you say there's this, the energies are random, but they're random except for this one state, which appears to be like an attractor state. It's the ground state. And when you do this, you miss the glass transition sort of disappears, and you get some sort of you get a surface which has sort of this glassy state here, and it drops down very quickly. So the idea is that this is now what you see as the classic picture in protein folding, is that you have this energy landscape which may not have any local minima, but you get to this glass transition, and when you change the temperature, you get these traps. You can either form the native state or you have discrete traps. And so there's a trade-off between energy and entropy. And what may be happening, and so it sort of proposed this idea in deep learning that because you're really not minimizing an energy, you're minimizing something like a free energy, there's a trade-off between energy and entropy. And when you design systems that have good energetics, they can overcome this glassy state and end up in this funneled landscape where you get very good results. An example would be something like, I try to think of like what would be an example of this. So it's a plausible thing to look at. I'm not claiming this is true. I'm just something to look at would be something like dark knowledge. In dark knowledge, there's this idea that you train a network, a multi-layer network with 2 layers of 800 each. You train it with 10 classes, you get 146 errors out of 10,000. That's kind of a typical error rate. It's not that good, actually. If you then retrain the model on something distilled, where you change the energy function, you change the loss function, that essentially you end up with, you go from 146 to 99. The model has the same entropy, it has the same capacity, but you change the loss function, you've learned the loss function. All you did was change the loss function in the model, and you end up with much lower results, much better, much lower number of errors. Another example would be something like adversarial deep networks, where one network is generating fake data and another network is trying to learn whether the data is fake or not. And the whole idea of the problem is that the discriminator, which is trying to learn what's fake, is trying to learn a complex loss function. You're not really changing and trying to modify the neural network. You're trying to just simply change the loss function to make it converge better. So this would be another possible example of an energy funnel. So, sorry, I'm running a little over because I kind of got a little tricky getting this thing. Well, anyway, the summary is that I've tried to give you some basic idea of what people think now is going on in some of the ideas going on around deep learning. Introduced something called the random energy model, which is a simple model. Talked about the glass transition and how that arises in the model. How you avoid the glass transition by having funneled energy landscapes, and a couple of possible examples, including dark knowledge and adversarial deep nets. There we go.